Thank you very much for the kind introduction. A little bit about myself. I'm from the German Aerospace Institute, from the group of the computational electrochemistry. And so we are a little bit more from the applied side and not too much from the theoretical side. And I want to start a little bit with the introduction and why we actually are using the Lattice-Boltzmann method. And that is because we are looking into batteries, and one of the production steps of the battery manufacturing process is the electrolyte filling. And there are multiple processes or multiple length scale that are relevant in the pore space that is on the micrometer that is relevant, but we also have binder material that holds together the various particles, and that is nanoporous. So we have already two length scales. And we want to fill and displace the gas with the electrolyte, and it would be great if it would be as simple as just sliding a blue box from a transparent background, but reality is not that simple, so we have to use the Lattice-Boltzmann method to actually simulate that. And another part that we are looking into is the nucleation process. So if we have a carbon particle, there can be nucleation points that then form to make crystals, and the nucleation points are on the nanometer, whereas the crystals are again on the micrometer. So we have these multiple length scales that we want to resolve at the same time. And for that, we have some previous research done, especially using the pseudopotential method in some homogenized porous media, where we use the partial bounce back or partial saturation method, or take whatever name you want for this method. And also we had to look into reactive boundary conditions. And both of them, I mentioned them because I want to say that they're both actually composite dynamics. And composite dynamics, that may be a little bit more of an unfamiliar term for you. But in general, it is just any dynamic that is consistent of like two parts. So for the partially saturation method, we have part of it is solid and part of it is fluid. And it's used in mostly two applications. One of them is smoothing the staircase effect of curved boundaries. Another one is to actually simulate directly some homogeneous flow. And in general, this is the collision operator that we are working with. We have a significant part that's fluid and some that is solid. And then we have this eta, which is also sometimes called the solid fraction in literature, that interpolates it between those two extremes. So we have one extreme pure bounce back, and then it's a solid, and on the other extreme, pure BGK, and then it is a fluid. And for my research in the reactions, I looked into like first order equilibrium reactions, and there I will generalize it to any kind of flux, because you can also look into it as a particulate flow or some kind of heat equations. And if you look into the equations over there, we see that there are some similarities. We have part of it can be described with an equilibrium scheme, and part of it with a bounce back. Noteworthy is that the interpolation factor this time around is going from -1 to 1. And so it actually goes from a no flux boundary condition with the bounce back to a Dirichlet kind of boundary condition with the equilibrium scheme and the bounce back together. So there are several open questions or annoyances that I have with these methods. First of all, it is really difficult to compare several of these implementations. And they also talk about the microscopic velocity and macroscopic velocity, and use the macroscopic for example, Darcy flow. And forces are, well, sometimes they have a prefactor and sometimes they don't, depending on which forcing scheme is used. So I wanted to know why exactly that is. And that is only for the partially saturated method, and for the flux boundary condition, there are several different papers, each of them actually generating their own boundary conditions. They actually don't really compare them each other, and it's really difficult to compare them. So this is why I set out to generalize these kind of composite dynamics. And I want to talk to you first about the theory, then I will circle back to the literature, see how with this framework that I created, we can look into this literature with a new sense of point of view, and then do some applications with that. And for that, I will introduce a new concept, which is a subpopulation. And effectively, I split the whole distribution into several other small ones. And we have then a fluid population as well as the solid population. For linear collision operators, which most of the collision operators are, we can say, yes, we can take out the prefactor, and case closed, we already have the partial saturation method. But where's the fun in that? So if we don't assume it's linear, or we go through the hard derivation, we get some more insights, which will actually answer the previous questions. Another part is that we have one fluid the subpopulation that applies onto a collision operator, and that applies for any kind of collision operator. And interestingly enough, and we'll also see that, you can have some cross collision operators, so that you can also have the solid population interacting in a fluid manner. And that can then explain how some of the other publications and literature actually describe the behavior. So in general, what we have from this is that we have the collision step that we modify. The streaming is untouched. Where in the collision step, we just sum up all the various interactions that we have with the collision term. And remember, we have some subpopulation, which we describe with this composite fraction, eta, and eta can be, is defined in one direction to always sum up to 1, because we don't want to go anywhere beyond 1, we don't want to create mass, and it should be between 0 and 1. So we already have some kind of conflict with the flux boundary condition, because that is going from -1 to 1. And then we have the part where each collision operator is only focusing on the subpopulation, so it interacts with the subpopulation density and velocity. So we need to define those. And we're starting off with the very familiar terms where we don't actually change anything, but those definitions are only true for fluid flow, where the momentum as well as the mass are conserved. In case that is not true, we actually have to consider that. And then we have these beautiful terms over there. And this becomes especially important for example bounce back. And if we have any kind of sources due to forcing or any other schemes, then we can just add them right there. And then for the cell total, we can just add all the subpopulation momentum and densities, and then we have that defined. And with this framework that is relatively simple and can actually fit on one slide, we can have another look into the literature and look at them from a new point of light. And for that, one of the first complaints is it's difficult to compare the various implementations, and we can actually tabulate them now with matrices. So we have the matrices of the subpopulations, and they interact on like this collision matrix. And then they are all applied to it, and then you sum up the collision matrix, and that's your collision operator in total. And it's really nice and fancy. Then there was this question about this microscopic and the macroscopic velocity. And for that, with this new approach to looking at it, the microscopic velocity is just the velocity used in the BGK collision operator. And then the macroscopic velocity that is usually talked in the papers is just the total cell velocity. And that is an important distinction because usually it is neglected that the solid part also has a velocity, and that becomes important in case you have moving boundaries. With this, you get this information for free. But if you look into the early papers, they had to write out the whole equations and put in the wall velocity manually. And finally, for the forces, because of how the interactions work, the velocity of the fluid is canceling out the prefactors. So if you use the Shan forcing, the force itself also, the prefactor of that is also canceled out. So if you use Shan forcing, you don't need a prefactor, even though there is one, because it cancels out. However, if you use Coué forcing, then you do need the prefactor. So all this confusion and regarding that is just cleared up. And for the flux boundary condition, I already mentioned that we have to somewhere ensure that the composite fraction stays between 0 and 1. And for that, I'm going to abuse a little bit of the collision operator, so I already am sorry. We can express the equilibrium scheme as the sum of the anti-bounce back plus the bounce back scheme, well, the average of those two. And if we plug that equilibrium scheme definition back into the flux boundary condition, we generate a new one where we directly interpolate between the anti-bounce back and the bounce back. So that is a very charming way of looking at it, because we can then use this information to extrapolate it to other scenarios. For example, we can implement wall velocities or any kind of other velocities into the equations directly without any kind of additional derivations. And we can replace the collision operators with physically equivalent ones. So for example, instead of bounce back, we can take the non-equilibrium bounce back if we want to. And with that, it is also, well, impartial to the lattices used. So you can use it for the reduced ones or for the larger ones. And that's also very nice because, especially for scalar fields, it's mostly developed for the reduced lattices. And with that, we can then play around with it a little bit. And I've mentioned that we had one problem that I wanted to solve, which is the nucleation, which is on the nanoscale and the microscale at the same time. Well, we have one voxel with one nuclei, and it's right there. It's tiny in comparison. And to accurately simulate it, we will use this composite dynamic approach. And we're going to use the flux boundary condition plus bounce back. So we average it effectively out over the voxel size. And to prove that this works, I will be using a simulative comparison where I simulate the same setup, but once with an alternating boundary condition between bounce back and fully reactive voxels, and once with this new continuous composite dynamics. And over here, we can already see that it actually works surprisingly well. In the back, so on the side, we have the Dirichlet boundary condition where we set it to 1, and on the other side we have some reactions going on. And with the alternating case, we can see that there are some, well, some valleys and peaks in the concentration near the wall. These fluctuations, they disappear over the whole course, and we don't actually see any differences a couple voxels away anymore, but it is quite prominent near the wall itself. And this becomes just larger and larger, the effect of it, the fewer voxels you actually have to deal with that are reactive. And to show that it is also working for not just 50-50, I introduce more and more bounce back voxels. And then we can see how much the concentration field has a deviation from it, and also how much the flux in total is deviating from the, well, the alternating benchmark. And we can see that the error itself on the concentration field is almost negligible. And I must say, with the spacing of 25, we have in total 3 voxels that are reactive compared to the 100 that are non-reactive. And even the flux error in that is only 1% difference, which is, in my case, is close enough, because if you use classical nucleation theory, 1% difference is damn accurate. So with that, you can also say that I played around too much with the composite fraction and tuned this problem to my specific case. That's not actually the case. The composite fraction that I used is just the amount of voxels that are reactive divided by the total amount of voxels. And that gives you an intuitive feel of what this composite fraction actually means. And that is just the chance that a certain population, a certain distribution is actually interacting as a certain collision. And with that in mind, that over here is a very simple answer. But if you have some kind of porous media, what is the chance that it behaves or interacts with a wall? That's a very difficult question. But in literature, it's often shown that there's only one composite fraction, and that's constant in all directions. And I want to play around with that a little bit and make some anisotropic flow through some porous media. And over here, we have some pressure-driven flow from the bottom left to the top right. And in this current simulation benchmark, I will show how the flow will look like from a perspective where we have some isotropic porosity. And we can see that the pressure is nicely falling off, and it's very nicely symmetric, and we have the velocity going equally through all the various outlets. However, in case we make the permeability in the x direction very low, so that we have only flow through the y-axis, we can see that the flow also really changes. We have some flow that goes, sneaks around the corners in the top and the bottom left, but the most flow is actually going through the y-axis. And we can make it also permeable in the y direction plus in the xy direction from the bottom left to the top right. And in that regard, we see that the flow actually follows that, and we can see that this flow over here is much more pronounced. We have much more flow in the x direction, but also that the contour lines are actually going more in this direction. And finally, we can completely put this on its head and make it permeable in the negative xy direction, so from the bottom right to the top left corner. And that we actually have some flow reversal, so that the flow from the bottom is preferentially flowing to the top left, so that we actually have almost no flow in the positive x direction. And with that, I already come to my summary. I have shown you a new way to think about, collision operators, how to add them, some kind of composite dynamics, and how that can be applied to reactive boundary conditions in addition to the more familiar partially saturated media. And for the outlook, there is some more work to be done, especially in relating the composite fraction to physical phenomena. And we extended this system to also to multi-phase flow. And usually you have to wait till the next conference next year to actually see about that. But my colleague is right there. He will present about that. I thank my funders and also for you for your attention. And if you have any questions, please ask them now. How do I define what? So the question is how I define if something is yeah. This one? So for the, I don't actually take the classical nucleation in here. I just want to show what happens after nucleation has happened. So usually if nucleation has happened, you create one nuclei, and that nuclei is in the order of nanometers, but you actually want to start simulating what the reactions are. And currently in the literature, it either is that you create a whole voxel and make that reactive and say the whole voxel is reactive, and then you have a huge error because, maybe only 1% of the voxel is reactive. And there are some approaches where they say, yes, we assume it's 50 or like 25% reactive till it covers everything, and then they convert it to a fully reactive part. But it's also, has only one step in between. Whereas with this, it's continuous. I can calculate what the precipitation rate is, what the coverage is, and from there, the composite fraction.
Is this method then using the superficial velocity or the actual velocity? Is there an exclusion volume from the model?
So at the moment, it's purely diffusion driven. And in the example that I showed there, it is just looking at the reactions that's happening and calculating the flux. So there is no velocity involved. But you can easily, since you know it is the anti-bounce back and the bounce back, and you know what the composite fraction is for that, you can easily extend it with the velocity. Mm-hmm. It is because we have so many different length scales. For example, the porous media that we are interested in is in the range of the micrometers. The pouch cell that we are simulating is in the range of centimeters. So if you have a 5 centimeter times 12 centimeter pouch cell, and then you need to compute what is happening on the nanometer scale, because there's one nuclei that is a couple thousands of voxel sizes too large to resolve.
Okay, then we should move on. Thank you very much again. And now we will get the follow-up talk on the root part, I guess.
Yeah, thank you for the introduction. Welcome to the DLR session of the day. So, my name is Benjamin Kellers. I work in the same group as Julius. And yeah, we are actually not Lattice-Boltzmann experts in the common sense, but we are actually battery experts. So we try to simulate battery systems. And as Julius already mentioned, I will show you the pseudopotential extension of the composite dynamics method. So first, I want to talk a bit about the regular pseudopotential method for the people who are not familiar with it. After that, I give you the actual motivation. Then we really extend the equations to composite dynamics. So I chose to do it this way around because you just have to believe the pseudopotential method, and then we extend it into a composite dynamic. You could go the other way around, but then you have to believe Julius already, and we start with composite dynamics and then extend it to multiple components or phases. But I think the most interesting part will be a few showcases and applications, and after that, a quick summary and outlook. So about pseudopotential methods in general, I didn't want to write down all the equations, but the main equation is actually the pseudopotential force. So as you can see from the form of this equation, the pseudopotential force is basically modeled by two pseudopotentials at two different positions that are interacting by this factor G. So you get an interaction strength. And what you can see there is the regular model, so no composite fraction added. We are now in a case where there's still only pure solid or pure fluid. I wrote down in the bottom what you actually do most of the time. So you set, for example, the pseudopotential to just the density of the fluid, and then you cancel or you set to 0 the equal terms so that you just have cross terms. That they have to be equal, that is basically optional. The interaction strength is just about the difference, actually, and you could tweak the stability of the model with this. But for a first time to think about it, we can assume it is that way. So now about the motivation. So we actually want to simulate the full steps in a battery production. So you have many different things going on, and my work is actually focused on the filling part. So once the electrodes are manufactured, they have to be filled with the liquid electrolyte. And we want to model this step because it is very difficult to investigate that with experiments. So nobody actually knows what is going on inside the battery once it is filled. There are many parameters influencing that, of course, and there are many observations you can draw from that. And we are actually doing both. We do the physical modeling and we write the software to then run the models. This was all done in the context of the Dsfd project, which was a very large Horizon 2020 project funded by the European Union. Here I wanted to highlight one of the main problems. So what you can see here is a stochastically generated battery cathode. And the blue material is the active chemical component. We call it the active material. The yellow material is, we already heard that in another session, is the binder material or carbon binder domain. There are some additives to it, but in a sense, it is the glue that holds everything together. And the problem with these glue particles is, as Julius already mentioned, they are nanoporous. So they are porous, but on a completely different scale than the cathode or the anode. And the problem is, we either need to resolve it, then we get billions of voxels, or we choose a composite dynamics approach, at least for the yellow part. So carbon binder domain is often a really large part of the total cathode. So you cannot just neglect it. The nanoporosity leads to the fact that the electrolyte is actually often so wettable that it can intrude the binder and can go through it. So these pathways are actually not blocked for the electrolyte. They just slow down the filling process. Yeah, wetting is typically very good for binders. You talk of contact angles as low as 8 degrees. And yeah, resolving is just not possible. Another thing in a battery, another component that behaves similarly is the separator. So between two electrodes, you have a separating material that blocks the electrical current. This is made of a similar material. So it is very nanoporous, there with the addition that it's often very anisotropic. So you have very directional flow paths that is done on purpose to let the ions through easily, but block everything else that could disturb the battery performance. Yeah, now to the extension to composite dynamics. This is actually really easy. We just need to add a few indices. As Julius already mentioned, I tried to choose a similar notation. So he labeled the dynamics with alpha and the component it is acting on with beta. And I just add that to my first equation. And then everything works basically automatically. What you have to keep in mind, this G factor is now a very large tensor. But in practice, most of its entries are 0. A lot of the interaction doesn't make sense. For example, bounce back has very few combinations that actually happen in real life. Another fact is, at the moment, I'm just interested in multi-component. So I don't need the fluid to interact with itself. So all the terms where K and L are equal are also dropped. So in the implementation, we don't have a huge tensor anymore. We just have a few G factors, basically. So then the Lattice-Boltzmann equation extension is also very easy. That has nothing to do with the composite dynamics. That is basically just adding the component label. So you solve now basically multiple lattices, in my case too. You have the electrolyte and you have the air phase or gas phase. Here I did a quick check or to convince you that it really works. So when you develop a new theory, it should include the old stuff as a limiting case. I just demonstrated it quickly. So if you go with the eta factors to full fluid and full solid, you really recover the old equation. Nothing interesting happening there, actually. The other case, fluid to full fluid, is even simpler. I didn't even write it down. But a main point you might be disturbed by is, in my whole talk, I never mentioned the boundary. And the boundary is actually what is for this multi-phase flow the most interesting part. So we want to get that right. And there are several techniques on how to model it. Mostly it is done with some kind of fictitious density inside the wall. because to really model the interaction with the wall, we don't want to add a third lattice for the solid or something. We want to derive it from the two fluid lattices. So to model the interaction with the wall, we put a fictitious density of the other fluid in the wall that the observed fluid can interact with, and then the contact angle is basically formed. But the question is always, what is this fictitious density? Because it is not really there. And I try to think of a really simple example. So imagine you have this bubble. It is drawn by hand. It is really simplified. You don't see any gradients. But let's zoom into two voxels. They are both fluid now. They're interacting with the interaction strength G fluid, and you just multiply by the two densities. So this is regular multi-component stuff. But now imagine you want to construct the same situation, but with a wall. So there's now a wall. What is happening then? Assuming the wall has the same interaction strength, we should put the fluid density inside the wall that was there in the first case. And it is actually the case that it is easily approximated from the surrounding area. So we don't really know the exact number, but we can approximate it from its surroundings. And this is what we actually do. And I want to show you some quick applications of the model. So one thing that the older models, even our older model, was never able to do is if you have a bubble, but inside a porous medium, you had always the same radius, because normally this fictitious density is constant everywhere. You use the same everywhere, and then all the bounce back components cancel out. They are the same in all directions, and this is why the bubble were not distinguishable by their size. We can now really distinguish them by the radius because we really model different bounce back interactions now. Here is another quick test. It should be a video. Yes, it works. This is just to show you what this eta factor actually does. So if you increase it and thereby increasing the solid part, you now have to imagine this drop is not inside air, it is inside a porous medium that is not resolved anymore. So the blue area is partially solid. And what you see, the more solid we make it, maybe I run it again, the slower everything runs, because it is basically just a restrictive force for the fluid flow. And another thing we did is something we call checkerboard. Here you can see if you use different eta factors, the fluid wants to be in the part that is favorable from its wettability. So if we have good wetting solid, it wants to be where there's more solid. If you have bad wetting solid, it wants to be where there's less solid. Here is some form of real-world application in 2D. I just generated a structure that looks very similar to a battery material with the binder added in yellow. And here you can see, in the beginning, we were only able to neglect the binder completely, that is the case on the left, or to make it fully solid, that is the case in the middle. And the case on the right is assuming it has 50% effect, it is 50% solid. And you see the completely different pattern. And these entrapments and how large they are and how many active surface area they block, that is actually key on how performant the battery will be once it's filled and once it's charged. So to summarize and give you a quick outlook, there exist many real-world applications. So I have a battery alone has two different applications. We want to homogenize the binder and we want to homogenize the separator. but many other problems are on multiple scales and would benefit from this homogenization scheme. The behavior of the non-resolved component, at least in our case, is key. You saw it in the last simulation. Everything is completely different if you don't treat it correctly. Composite dynamics with pseudopotential coupling are necessary to model that. Otherwise, we get into billions of voxels. An improved boundary condition, as I showed you, can enhance the accuracy. So it not only gives you the effect with the bubble radii, it also models better contact angles. So the nice thing is for 0 extra computation costs, because we actually use Palabos and the full-way bounce-back scheme. So the populations we use to estimate the density are actually there. They are just thrown away in the next step, and we started using them. So with that, I want to thank the funding agencies and our partners, and Palabos for making the code available. And I used POROUS and Scikit-Image to generate some of the structures you saw. Thank you.
Question.
We did some first checks, but before we say it is, we want to check it a little bit more. And it will be included in an upcoming publication. So if you look for it in a couple of months, you should be able to read about it.
What happens to the actual volume of the second phase fluid in the form? Not really thought because
that is actually a tricky question, and we are discussing about that for a month now. So if any one of you has a good idea, please share it with us. The problem is, maybe your question is going to this. Once you have this homogenization or composite dynamic schemes where a cell can be partially solid or partially fluid, you have no idea anymore how to interpret what you're actually shifting around. Is it still a real density? Is a density that comes from a fully fluid cell the same in a partially fluid cell? Or do we have to make some conversions to keep everything nice? So
that's my question from before. There is a superficial density and velocity and the action. You are going to say the same thing, right?
Yeah, I just want to rephrase his question. Not curiosity, what about permeability?
yeah. So Julius already mentioned we have to interpret the eta factors of the probability of the fluid part interacting with this dynamic or with the other dynamic. And for fluid flow problems, like you see here in the battery filling, it might be that permeability is a much better physical property to use. So it is not that we say, so you don't have to, you should not confuse the composite fraction with the volume fraction of the material. There is not necessarily a one-to-one correspondence. So really be careful with it. In these reactions, it works really well because if you have a reactive surface, this is basically one-to-one. So your chance to hit a reactive part is exactly the volume fraction of the reactive material. In fluid flow, it is not. We don't even know if the 0 component of the population is treated equally. So we had the idea around that maybe the 0 component is experiencing more something like tortuosity, and the ones that are really leaving the cell are more related to permeability, but we are still working on it.
Thank you again.
Hello.
What's your on? It is on, don't worry.
Okay. Many thanks for the introduction. So it's my great pleasure to share my work here. My topic is a post-scale study of effects of heterogeneities on the operation of porous medium. And I'm Lin Fei from ETH Zurich. So this is the outline today. And first is the background. I would say operation in porous medium is ubiquitous phenomena in nature and industrial applications, like the water management of the fuel cells, like introduced by the previous two speakers, and also the saline evaporation and soil precipitation in geological carbon storage. And moreover, we can also use this technique to do thermal protection, like used in aerospace engineering field. So the key question is how to make the evaporation rate as fast as possible. So we will give you some hints based on lattice Boltzmann simulations. And as you know, the evaporation is liquid gas phase change phenomena. So I will first present you some phase change phenomena simulated by lattice Boltzmann method in the last years. So I don't want to go deep into the methods. I just show you the main idea. We use cascaded lattice Boltzmann method for the flow field. We use pseudo-potential model to do the phase separation, and we use finite difference method to solve the temperature field, and we use non-ideal gas equation of state to couple the temperature field and the flow field. And we have used this method to simulate droplet evaporation for boiling and convective boiling phenomena. However, all these phenomena are in single component system, which means that we have only one component, and it has two phases, the liquid water and the water vapor. And today we want to talk about simulating two-component, two-phase evaporation phenomena in porous medium. So the idea is that we have the air component and the water component. For the liquid phase, the air can be dissolved in water, but not so significantly. And for the gas phase, we have a mixture of water vapor and dry air. And the mass fraction of the water vapor can be changed within a wide range of within a wide range. So it is almost corresponding to a real case. And the air is a single phase component using ideal gas equation of state. And water is a two-phase component. We have liquid phase and vapor phase, and we use Pound-Robinson equation of state. And we can simulate both isothermal and non-isothermal. But today I will limit it to isothermal case, and we use cascaded collation operator. And this is a model validation. So we simulate the drying of such a microfluidic system, and we make a comparison between our simulation results and the experiments. And as you can see, we can achieve a good agreement with the experiments. And we also made a quantitatively comparison, and the agreement is also very good. And then this is a numerical setup we used here. So we designed such a dual porosity porous medium. So we fill small cylinders in the middle. It produces a larger porosity, and we use larger cylinders on the sides. So the porosity there is smaller. And we have a gas inflow on the top right channel, and we have outflow on the right. And for the inflow, it is a gas mixture with a dry air and water vapor. And we can change the Reynolds number, and we can also change the vapor concentration and also contact angle. And here I show you some results. So this is a case with Reynolds number 100 and contact angle 20. As you can see, we can simulate all the post-scale information like the liquid field and also the vapor concentration field. And as you can see here, for the evaporation case, generally larger pores dry fast, which is induced by the so-called capillary pumping effect, because the larger pores, so they have smaller capillary pressure. Therefore, if the gas pressure is constant, So the liquid pressure in the middle larger pores is larger, and this pressure will pump the liquid to the smaller pores. Therefore, the liquid phase in the smaller pores are pinned for a long time. And here I introduce the so-called drying curve. So the change of the evaporation rate with liquid saturation. So from experience, actually for drying a porous medium, so there will be 3 different periods. In the beginning, because we have a lot of liquid phase, the evaporation is fast and almost constant. It is called the constant rate period, CRP. And when large pores are dried out, this drying rate is decreased significantly. It is the second phase, FRP, falling rate period. And in the third case, the liquid gas interface is receding deeply into the porous medium. It is called the receding front period, RFP, and reproduce such phenomena as in experiments. And moreover, we have done a lot of simulation by playing with the contact angle, the inflow vapor concentration, and also the Reynolds number. Because CRP is usually most important, so we studied the average evaporation rate in CRP, and we found a universal scaling law. So as shown here, it works quite well within a wide parameter range. And our aim is to, enhance the drying rate or evaporation rate, right? So one method is that we further increase this average evaporation rate in CRP. But however, from this governing equation or this scaling law, actually it is nonlinear. So after a certain parameter range, the system will go to the limited regime. So we cannot increase it furthermore. So another strategy is to extend the range of the CRP, right? So we will use the heterogeneity in the following. And we want to start from the maximum evaporation rate up to now as a reference. So this is a starting point from the following. So we consider the porous medium. We divided the system into 2 layers. So we have a top layer and bottom layer. They have different contact angles. So as shown in the 3 movies, you can see they may have different evaporation behaviors. And in the end, you can see the residual liquid mass. And from the 3 cases, actually, you can see by decreasing top contact angle from 45 degrees to 15 degrees, or increasing the bottom contact angle from 15 to 45 degrees, the global drying rate can be improved, right? So why? So this is explained based on post-scale analysis. So let's look at the 2 moments. The moment 1 just before the liquid gas interface, just before arriving the border, it is the red curve. And another moment is the liquid gas interface just after arriving the border. It is the green curve. So if we look at the pressure difference at the 2 moments, we can see from very basic calculation, if the bottom contact angle is higher, so there will be a positive jump of this delta P, which means that our system will get a refueling. So if you look at the small pores on the side, so actually we refill some liquid water, so as shown in this green arrow. And if we have a larger bottom contact angle, actually this refueling is stronger and stronger. So that's why the evaporation rate is increased. And if we look at the transition from CRP to FRP, actually, we define the transition as the point where one of the larger pores, a smaller pore is dried out. So let's look at here. So this is the transition point. Actually, from case A to C, the transition saturation is decreased. So which means we have prolonged the CRP. However, one special case is the last case. Here we have very big contact angle differences, and which leads to a breakup of liquid connection. Therefore, the liquid cannot be supplied to the small pores anymore. Therefore, the transition S is increased again. So if we look at the evaporation curves, actually, by decreasing theta top or increasing theta bottom, we can generally change the transition saturation from here to here. So which means the evaporation rate is increased, except for the special case where we have big difference, contact angle difference, because we have a disconnection. And so here, after this point, we have a jump of the evaporation rate. That is because of the refueling phenomena I introduced previously. Then let's look at another case. Now we have a uniform contact angle throughout the system, but we have different pore size. So here we have vertically uniform pore size. Here, let's look at the bottom. We have smaller cylinders, therefore we have larger pore size in the bottom. But here we have smaller pores in the bottom part. And in the end, you can see actually the residual mass here is less than the other two cases, which means that by increasing the bottom pore size, the global drying rate can be improved. Actually, this can be also explained based on post-scale analysis of the pressure difference. And if we have larger bottom pore size, actually we have positive pressure jump. Therefore, we will have refueling as shown in figure A. Otherwise, we will have receding here on figure B. Therefore, case A is better. And therefore, the transition saturation in case A is also smaller. And among the three, you can see actually the porous medium 3 with larger pores in the bottom is generally faster than the other two cases. So now we have considered two cases. The first case, we have porous medium 1, but we have different contact angles on the top and bottom. And then we consider three different porous medium. We split the porous medium into two parts, and they have different pore size, but we use uniform contact angle. We found that if the contact angle on the bottom is larger or pore size in the bottom is larger, the drying is faster. So the question is, can we combine these two factors? Say we're using 3 or 4 layers, multi-layers, and with different pore size, different contact angles. And here is a case in porous medium 6. We have 4 layers, so with increasing pore size from top to bottom, and also increased contact angle from top to bottom. So this is 15 degree, 45 degree, 75 degree, and 105. And you can see the evaporation pattern is very well defined. So there are 2 stages. In the first stage, the evaporation front penetrates the porous medium in the middle, and then it expands horizontally and moves backward. It is, let's look at the movie again. So it expands and moves backward. So if we look at the post-scale information, actually, so when the liquid gas interface moves from this layer to this layer, and second layer to the third, and from the third to the fourth, actually we have a cascaded refueling. Therefore, we have a very strong refueling in the small pores, so which can increase the evaporation rate. And then if we look at the transition saturation from CRP to FRP, it is also decreased to be a very small value. So now the transition is around 0.17, much lower than before. And then if we look at the evaporation rate, so you can see the transition saturation is changed from like 0.45 to 0.17, and the evaporation rate is increasing again and again, so with multiple layers. This is very interesting. And we have also done 3D simulations as compared here. So the left-hand side is the reference case with uniform contact angle and uniform pore size. Right-hand side is the optimized case. We have increase in pore size and increased contact angle. As you can see, the right-hand side case is much faster than the left-hand side case. And then we can look at the acceleration or the speed up factor. We consider the time needed to reach a certain saturation. So we consider the time ratio, so between the reference case and the optimized case. So if this ratio is larger than 1, which means we have a speed up of the evaporation, right? So as you can see, to reach a smaller and smaller saturation, this acceleration is more and more significant. And for example, if we want to evaporate 95% of the liquid in the porous medium, actually we can obtain a 4 times acceleration or speed up. So previously, we considered the porous medium with the same size and the same porosity. Now I found that if the porous medium is bigger, this pattern is also robust and even more robust. So here we have a larger porous medium. We have 5 layers. As you can see, we also have this pattern. Anyway. So it penetrates in the middle and then expands and then moves backward. And for this case, we can even achieve a speed up factor of 5 times. So let's go to the summary. I found based on lattice Boltzmann simulation, if we want to do evaporation in porous medium, if we have larger pore size or larger contact angle in the bottom, actually we can increase the evaporation rate. This is due to a pressure jump at the interface of the 2 parts. And we can combine these 2 heterogeneities. And then we found that the evaporation experienced 2 well-organized stages. In the first stage, the evaporation front first penetrates in the middle. In the second stage, it expands fast horizontally and then moves backward. And the multiple capillary pressure jump in the first stage will lead to cascaded refilling of the small pores and therefore successive increase in the evaporation rate. And the strong capillary pumping effect in the second stage will prolong the duration of CRP significantly. So compared with the reference case, already the maximum evaporation rate achieved before. So the optimized case can prolong the CRP from S equals to 0.64 to S larger than 0.12. And we can achieve a speed up 5 times to dry out 95% of the initial water. And many thanks for your attention. I'd like to address your questions. Yeah. Yes. 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 Oh, sorry. Translation what? Yes. 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 Transition. You mean in the very beginning, the you mean this curve? You mean this curve? Yeah. Do you mean there's like a transition of the slope in this curve? Yes. 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 No, this is because we have capillary pumping, so the liquid is supplied from the larger pores to the small pores. So the small pores in the channel level is always filled with liquid phase. So that's why in the first stage, the drying is very fast. The drop of this curve is very fast. Sorry, I cannot follow you very well. What do you mean by same size? They are different size. The size are different. For the same size, no. We will not have this transition. No. Yeah, it's just decreasing. Yes. Yes. Yes.
Any more questions?
Yeah, yeah. Yeah, so because we want to make use of the capillary pumping effect, we want to pump the liquid from the larger pores to the small pores, so we use hydrophilic. So if you use hydrophobic, actually the pumping is from the small pores to the larger pores. So it will be, so the evaporation rate will be lower. I will show you, because I don't show you the movie for the bottom hydrophobic case. Okay, I have the movie. Because it's slightly hydrophobic, I would say it's not very, very hydrophobic. You mean this case? Let's go back to the movie. So you mean here? Yeah, it's somehow hydrophobic if you look at how to. Sorry, I don't know how to stop this movie. But anyway, yeah, if you look at the snapshot, I think it's hydrophobic. Yeah. Yeah, please. Reynolds number is defined based on the inflow peak velocity and the gas viscosity and the channel length scale, not in porous medium.
Can you somehow estimate the importance of inertia effects inside the porous medium?
Inside porous medium, we usually don't talk about the Reynolds number. We care more about the capillary number. It's very small. It's in the order of 10 to the power -3 or 10 to the power -4.
Okay, then thank you again.
Thank you.
Hello. I have a question. So for my presentation, I uploaded 2 presentations. I want to ask if